Okay, next, let's see if we can apply control approximations, semi-gradient methods, for off-policy control. So in off-policy learning, we seek to learn a value function for a target policy, pi, given transition sampled from a different behavior policy B, right? In the prediction case, both policies are static and given, and we seek to learn either state value or action value. In the prediction case, that is not the control case. We're not trying to learn a new policy. In the control case, however, action values are learned and both policies typically change during learning. Pi being the greedy policy with respect to Q hat, to our approximation, right? Pi is the policy that we're trying to converge on, to learn for, and B, the behavior policy, being more exploratory, such as epsilon greedy policy with respect to Q hat. Now, of course, we can, as before, we can simply use on-policy algorithms with importance sampling in order to make them off-policy. And the importance sampling, the trick from importance sampling that we saw previously for the non-approximation cases can easily be extended for the approximation case, for both in Monte Carlo approaches, TD0 with approximation, and n-step bootstrapping with approximation. We simply multiply the TD error, or our approximation error, by the importance sampling ratio as before. So the same theory and the same practice holds for the approximation case and can be applied. However, when we do off-policy approximation, we are in danger of encountering divergence in learning. This is because with a function approximation, the distribution of updates does not match the on-policy distribution, right, in off-policy learning. That is, updating one state might affect the value of many others. And so semi-gradient and other simple algorithms are unstable and often diverge. For instance, consider the two states and a value approximator with one tunable parameter. Okay, so let's assume that we can only tune the W parameter. Now, and we approximate one state, the first state, the one on the left, as W, and the one on the right as 2W. And you might say, well, this is not a great approximator because it can fit only very specific data, right? Just cases where the left or the state on the right has twice the value as the state on the left. That's true, but whatever the values are, there is some W that best fits the data. Right? I can find the W that is the best fit, is the closest fit to whatever values are assigned to these two states. The problem is that we won't be able, in many cases, we won't be able to converge on that value, on the optimal value for this approximation problem, right? So we can't approximate approximate it perfectly, but I'm telling you that we can't even find the optimal W. We can't converge on it because in many cases, if we want to be very careful, we'll just update W's to infinities, I don't know, or minus infinity or something like that. Divergence in learning. This is because updating the value for the left state, for instance, would also increase the value for the right state, which will increase the value in the left state, and so on. We might have some feedback effect, okay, that will just go to infinity. And this can be illustrated in a simple scenario, a bit more complicated than the previous scenario, but still there's a nice static scenario that demonstrate this process. So if you consider the MDP that we see here on the screen, and a specific approximation, a specific value approximation, you can see the approximation for each one of the states inside the circle, right? So for instance, Vk of S here, our approximation at any iteration k, don't worry about the k now, would be some parameter θ7, it's one of our tunable parameter, plus twice θ1, which is another tunable parameter. The interesting thing to note about this specific MDP, first of all, it has linear value approximator for all of the states, right? You can see it here at inside each one of the states. But more than that, there is an exact assignment. There is a solution to these tunable parameters that result in accurate approximation. Okay, so there exists a solution to these tunable parameters such that the approximation is accurate, has zero error. Okay, so for instance, the estimated value for the... Oh, sorry, okay. Yeah, I already said that. So the rewards in these MDPs are zero on all transitions. So the state value for all transitions should equal zero. And as I said before, this can be exactly approximated, right? If we set all of the tunable parameters to be zero, then our approximation is accurate. We can, hopefully we can reach it. Now I'll show you that with semi-gradient methods, we won't be able to reach this optimal solution, and a very simple solution. So semi-gradient TD0 methods will cause weights to diverge to infinity, in this case, or to minus infinity. Okay, although a very simple solution exists. So let's assume that we initialize the... Of course, if we initialize the tunable parameters correctly to zero, it will be a fixed point, it will stay there. But let's assume that we initialize it as follows, right? As ones, except for θ6, which is set to 10. Okay, so θ6 is initialized to 10. And let's assume an alpha of 0.1 and a gamma of 0.99. And so, in this case, you can see that, for instance, V0, our approximation for the bottom state here, would be 2 times 1 plus 10, it will be 12. And for any other state that is not the bottom state, our current approximation, our initial approximation is 3. Okay? Now let's say that we sample a trajectory, start at some S0, let's say the left state, this one. And we start there, we perform an action down, there's only one action to take, and we observe an immediate reward of 0, and we reach state, the bottom state, and after that we terminate the episode. Okay, now based on this transition, S0, R1, S1, we update our approximation. And again, we use the semi-gradient definition to update the values, right? So it will be R1 minus gamma times the approximated value of bottom minus the approximated value in S0 in our case. And we multiply that by the gradient of our approximation. So this will result in a new value for θ7, which is 1.89, and we update also θ1, right? These are the two tunable parameters at the leftmost state. And the new value will now be 2.78. So you can see that we increased both θ1 and θ7. We increased their values. So now at the next iteration we have some updated values, larger values, which will impact, these values will impact also the approximated value in the bottom state, right? So we updated actually the approximation for our top state here on the left, but it also impacted the next state, the bottom state, which impacts our update to the top state, right? And actually you can see now that all of the state values were updated upwards, given this iteration. And actually, if we continue this process, we'll see some divergence in the values for both all of the tunable parameters 1 to 5, but also to tunable parameter 7, right, the rightmost one, and also to tunable parameter 6. So they'll all start oscillating and going out of control and going to infinity. Although, as I said previously, there is a very simple solution for this approximation problem. Right, and so you can see how this type of approximation can lead to divergence and can often suffer from this issue.